This week, we are talking about time averages of random processes and ergodicity. And then we will talk about spectral analysis. We will define the periodogram estimate of a random process. And based on this, we will define power spectral density. We will look at the properties of the power spectral density. And finally, we will talk about response of LTI systems to white sense stationary random signal or random processes. Okay, so we'll start with time averages of random processes. And why do we need this? The first observation here is in many cases, parameters of a random process are not readily available for us. Okay, they must be obtained through measurement if that is possible. And by the parameters, I mean the mean of a random process or the autocorrelation function or the variance, etc., or the shape of the distribution with respect to time, if you can have that. And of course, with measurements, you have limited observations. You cannot cover the entire time axis. You cannot repeat some random experiments, etc. But of course, with repeated time experiments, if you can do it, if you can repeat a random experiment, you can obtain an average. Okay, if you remember, we did this for a sequence of IID random variables, right? We wanted to estimate the mean of, for instance, an IID random variable sequence, and for this we used the sample mean. If you remember, this was the sample mean, okay? And whatever observations you have, you add them up, you divide the sum by the number of observations, and what you have is what we call the sample mean. And if you remember, we analyzed this, and we had seen that this was an unbiased estimator because its mean was equal to the true mean, and then we looked at its variance, etc., and then we arrived at the weak law of large numbers. And in the same spirit, the mean of a random process, now we are talking about a random process, not a sequence of random variables, but essentially they are quite similar. So we apply the same reasoning, and we would like to estimate the mean of a random process, okay, using a sample mean, okay? So if you observe your random process at the same time instant, over and over again. So what does that mean? Okay, so that means your process is suitable for restarts. Okay, so you start performing your random experiment, and at time t, let's say some specific time instant, you observe it, record its value, and then you reset your environment. Okay, you restart your random experiment, observe it at the same time instant with respect to your new origin. Okay, and then you record that value, that becomes x2t, whatever that is, and then you repeat it, x3t, x4t, etc. So you repeat this n times, okay, and then take the average of your observations. That will give you a sample mean for the expected value of this random process at time t. Okay, remember, in general, the mean of a random process depends on time, but in this way, if your random process is suitable, if you can reset it, if you can run it multiple times, then you can do this. Here, of course, I represents the experiment number, but the problem is you cannot repeat all random experiments. For instance, physical phenomena, really, you may not be able to repeat them very accurately, at least. For instance, for a coin toss, which will give you an IID Bernoulli sequence in general, you can repeat this because, well, the definition of time depends on you. Well, whatever however many times you toss the coin, that defines the round of this random process. Okay, so the time is defined by yourself. So you can repeat it at any time, you can reset it at any time you like. Therefore, it is repeatable. But for instance, a temperature measurement, even if you measure the temperature at a specific point, let's say at the same instant every day, it's not the same process, right? We all know it's not exactly the same process because there is, of course, variations in temperature with respect to a lot of parameters, let's say. So it will not be the same process, okay? It will be a close measurement in general, but it's not going to be a repeated experiment. So what to do in that case? What you can do is compute a time average. Instead of a sample observation average, compute a time average. That is the best you can, right? That is the only thing you can do. Because, well, if you cannot repeat it, you have one single observation throughout the entire time axis. Okay, you cannot do anything else. You can only compute a time average. So what is that? You observe this random process within an interval, which we call minus t to t. Well, depends on the placement of the origin. So minus t doesn't necessarily define uh, past and positive times, doesn't necessarily indicate future observations. Here, it's just a representation of your interval. So by a time average, we refer to this quantity. If the process is continuous time, you integrate your observation. I'm assuming you are observing it continuously. So you have x of t throughout this interval from minus t up to t. So you integrate it and then you normalize it by the width of the interval, which is 2t. And that gives you this, which we call the time average. Okay. Similarly, if your process is discrete time, of course, you can define this. You're observing your random process for the rounds from minus n up to plus n. That gives you 2n plus 1 because you also have the 0 observation. 2n plus 1 observations. So you take the average of these, and then what you get is the time average of this discrete time process. Now, what is ergodicity? Ergodicity is the time average converges to the true mean. If that is the case, we call a process mean ergodic. And an ergodic theorem gives us the conditions, okay, under which the time average defined in this way and this way for the suitable random process, okay, converges as the observation interval, and essentially t, becomes large, okay? So we will see a few examples for ergodic theorems, and essentially you can define this not only for the mean, but also other statistics like autocorrelation, etc. So an ergodic theorem will be a theorem stating the set of conditions under which this time average really converges to the true mean value.